So thank you for joining me on a whirlwind tour of lenses. As you've probably already guessed, I am does this thing work? I'm this Joshua Grosso guy, and thanks for spending the next 10 minutes with me. So first on the agenda, what problem do lenses solve? Next, we'll look at how to create, use, and compose lenses, and then finally we'll package it all up in a real-world example. And then we'll be ready to learn how to take what we've learned to the next level. My examples will be in Haskell and use the lens package, but the concepts we're going to cover will be applicable to any other language or implementation of lenses you're going to come across. So let's jump right in. Why do we need lenses? 3 words: nested data structures. Think records within tuples, within lists, within more records, etc. As monolithic state becomes more popular, which is where your application's whole state is stored in a single object, like an Elman redux, I'd say it's probably fair to assume that manipulating nested data structures is going to start becoming more of a concern in plenty of situations. And most languages solve this problem by encouraging mutation and impurity. As we all know, imperative code is gross, though, and we'll see how to get something even better and remain completely pure. So here are some data structures I whipped up. We have our game state, which has a player and a world. Our player has a backpack and a full name. Our backpack has a capacity and a list of contents, and our world has a list of enemies and the level number. So nothing fancy going on here. So you're an enterprising Dovahkiin and you've just scored yourself a shiny new Dragon Soul. We need to know your backpack's capacity to check if we can shove this into your backpack's contents, let's say. So let's see how we can get that out of our game state. Well, we know that defining a record in Haskell creates these accessor functions that we can chain together to extract something from our game state. This is clean and easy to understand. The code to set and modify a value inside our nested data structure, on the other hand, is ugly. I forgot to bring barf bags for you all. Sorry about that. There's so much boilerplate. It's really hard to read, and it's going to be tedious to modify if the record structure changes. Better yet, it actually grows exponentially as we add each new layer of nesting. This is not fun to work with. And now for the final nail in the coffin. Wait for it. A traditional imperative language is nicer than Haskell. I mean, which would you rather type? This is a horrible problem. You can basically all just leave Boulder and go home now, because Haskell's been defeated by C# and we've just got nothing left to live for. But all is not lost. What if I told you that we could make the Haskell code look like the C# and remain purely functional? So let's go into la-la land for a moment and imagine what that might look like. One possible solution is to make a consistent way to get, set, and modify, instead of having that special case gross code for setting and modifying. In this particular API, each operation has its own helper function. I didn't just pick this out of a hat, though. As you might have guessed, this is what lenses provide us with. So we're going to dive into this, but what would this have looked like if we had used it in our earlier example? The first example is so much cleaner, and I'm sure we'd all much rather work with it than the second one. But now for the real test. Let's compare our Haskell code with lenses to our C# from earlier to see how we're stacking up against that competition. And behold the magic of lenses, which let our Haskell code beat our C# code in conciseness. So it's time to dive in and learn exactly how this all works. Let's start with the very basics. How do we create a lens? With the lens package, we are given a make lenses function, which uses template Haskell, basically Haskell that writes more Haskell. This is about what it looks like. We create a record definition, and we apply make lenses to it. The 2 apostrophes are not standard Haskell syntax. That's part of template Haskell. What it will do is automatically define lenses from a record declaration called player and world. So that's all it takes to make some of these lenses. Let's see how to use them. To get from our data structure, we have a function traditionally called view. And it takes 2 things, a lens and a data structure. In this example, our lens is player, the player lens we just created, and our data structure is some game state we've probably got lying around. So what view will do is reach into our game state, grab whatever our player lens is focusing on, pull that out, and hand it to us. So in this case, view will return just a player. And this is how we did it before. So we don't really have a great readability benefit yet, But this is where it starts to get fun. Because to set inside our data structure, we have a function called set. Big surprise there with a name, which takes three things: a lens, a new value that we want to use, and again, our data structure. So what we're doing in this case is we're focusing in on our player part of our game state. We're getting rid of whatever used to be there and replacing that with the value of new player. And what set will do is give us back a modified game state. And this is how we would do that before, if you're familiar with Haskell. A modifier is related to set. That's if we want to apply, instead of just totally throwing something out and shoving something else in, if we want to modify what's already there with a function and use that instead. We can define this just in terms of a getter and setter. Get a value out, apply a function to it, and set that result as the new value. But lens packages define the over function for us so we don't have to. It works like so. It's pretty similar to set. It takes three things again: a lens, a modifier function, and our data structure. So it's going to reach into our data structure, pull out whatever the lens is focusing on, apply our function to it, put that in instead, and hand that whole data structure back to us. So in this case, we're going to rip out the value of lens, apply the modifier player function to it, and set that as the new value of player. So we know how to use lenses a little bit, but we haven't quite yet tackled the problem that we set out to solve, though. How do we manipulate nested data structures with lenses? One way is to build up a chain, like so. This really only works for getters, though. For setters and modifiers, it's still really tedious. We're back at square one. The code doesn't even fit on the screen. This is where lenses really shine, though, because they've got an awesome trick up their sleeve: lens composition. In Haskell, that's actually done with just plain old normal function composition, but it might look a little different depending on the language or implementation that you're using. If we compose two or more lenses, we actually get a new lens back. So in this case, we're composing our player, backpack, and capacity lenses to get back a single composite lens that, given a game state, will focus all the way into that part of our data structure and let us manipulate it directly. And here are some examples of what that might look like. And a neat syntactic trick is to remove the spaces around the operators to mimic mainstream imperative languages. And so far, we've been using auto-generated lenses, but we can't always. Let's say that we want to define a brand spanking new two-tuple type called pair. Since this isn't a record declaration, we can't use make lenses because it won't know what names to give each part of our lenses. But how can we define lenses to focus in on the first and second items of this data structure? Well, let's see if there's a function that takes a getter and a setter and packages them up for us. As it turns out, the lens package provides a lens function. The names are really original in this package, as you might have seen. It just takes a getter and a setter, turns them into a lens for us. So lenses are pretty simple the concept behind them is pretty simple. They package up a getter and a setter for us, and boom, if you can give those to me, I can give you back a lens. I've named these lenses _1 and _2 to mimic the names in the lens package for the first and second items of built-in tuples, and we're going to see those in action later. So now for the fun part. Let's see how we would write each line of this earlier C# example using lenses. So for the first line, we are applying a function to the player's backpack contents. We're basically adding Dragon Soul to the end of the list. So since we're doing some modification with the function, over is the helper function that we're going to go for in this case. Our first argument is the lens, the composition of player, backpack, and contents. It looks pretty similar to the player backpack contents up here with the dots. A modification function, just add Dragon Soul to the end of the list, pretty simple. And our data structure is some game state. And what this whole thing will do is hand us back a modified game state with this change made to it. So for the second line, what we're doing is just wholesale replacing a value with a new one. We don't care what used to be in the second item of the player's name tuple. We're just going to replace it with something else. So set is the function that we're looking for. Our lens is the composition of player, name, and _2. That's that tuple lens that I was talking about from earlier. Our new value is just the string the brave, and our data structure is some game state. And again, this is going to hand us back a modified version of our game state. For the third line, we are dropping the first element from the world's list of enemies. In C# with link, we would write that as skip1. In Haskell, we simply know this as tail. So again, we're applying a function, and over is what we're looking for. Our lens is the composition of world and enemies. Our modification function, like we've said, is tail, and our data structure is some game state. And again, this returns a modified game state. For the last line, we're not doing anything really special here. We're just incrementing our world's level number by 1, so it's just like the other times we've used over to modify our game state. Ta-da! You're now able to use lenses in your own code. I'd give you all certificates, but paper is expensive. Typing view, set, and over all the time can get tedious, though, so the lens package provides some infix operators. Here's the code we just wrote without operators, and here it is with operators. It's a bit more concise and looks more like an imperative language, which is nice because we can reuse intuition that we might have if we're coming from an imperative background, like many of us probably did. So now that we know how to independently translate each of those C# lines into Haskell, we're still missing one crucial step. We need to simulate the imperativeness of the original code, where we perform one step, and then the next, and then the next, to end up with some final result. Well, we can just chain our lens operations together, like so. We're applying this to some game state we've got, take the result of that, pass it into the third line here, which is the set, take that, pass it into the over, and take that and pass it into our final over to end up with some composite result that has all these operations applied to it in order. And if we write this with operators, if you recall, this was our example from the beginning of how Haskell beats C#, so pat yourselves in the back because we did it. So we've just scratched the surface of the power of optics. We've only covered lenses, but there are also prisms, traversals, folds, and ISOs, which all have unique abilities. And if you're interested in how these lenses work under the hood, there are two major implementations you might want to check out. Van Laarhoven lenses and the new kid on the block, Profunctor optics. You can just skip Profunctor optics after Paul Phillips' keynote this morning, go straight for Profunctor nuclei, whatever those are. I don't know. And I will post these slides on Slack for your viewing pleasure. Feel free to ask me anything anytime. My email is jgrosso1@asu.edu. Thank you.